In the last lecture, we started our discussion on the topic of finding optimality conditions for constrained optimization problems. Now, towards this, in this lecture, we will talk about three special cones that will be useful later on in finding optimality conditions for constrained optimization problems. The cones that we shall be talking in this lecture are the cone of feasible directions, the cone of descent directions, and the linearizing cone.
On the last day, we started our discussion towards identifying optimality condition for constraint optimization problems. And in the last lecture, we were trying to discuss, we were revisiting the Lagrange's multiplier rules, and we have found that there are two specific points for which we need to be careful while applying Lagrange's multiplier rule. Otherwise, the rule might be giving a misleading conclusion. And in order to enhance the ability of the Lagrange's multiplier rule, we were mentioning that there are few cones which will play central role in identifying optimality condition with the help of the Lagrange's multiplier rule for constraint optimization problems. Fine. And on the last day, we could discuss only one particular notion of cone, that was the dual cone. For a given set capital C, we have defined what is the meaning, what is the geometry, a few examples on the dual cone. In today's class, we shall continue the discussion on the cones for constraint optimization. At first, we will discuss the cones for feasible directions, then the linearizing cone and the cone of descent directions will be discussed. And afterwards, once we finish the portion of cones of descent directions, we will be at a position to find at least one geometric necessary optimality condition. And once we find that geometric necessary optimality condition, then we will try to discuss about the notion of tangent cone, and with the help of the tangent cone, we will see that the most efficient optimality condition can be identified. Well, so after the first three notions of the cones, we will have a geometric necessary optimality condition. Necessary optimality condition for constraint optimization problem. For constraint optimization problem. Now, in order to discuss the idea of cone of feasible directions, we will have to start with the idea of constraint optimization. Let me at first mention the generic nature of a constraint optimization problem, generic presentation, and a few terminologies related to constraint optimization problems. By a constraint optimization problem, we mean the following problem. In which we have to minimize a function f subject to a set of inequality and equality constraints. Let us suppose we have m many inequalities in the problem and we have l many equality constraints, and here the variable x is assumed to lie on an abstract set capital X. This capital X is a subset of the n-dimensional Euclidean space, and usually inside of capital X those constraints are kept for which it is difficult to identify one inequality or equality to present those constraints. Or capital X typically can also be considered to be the entire n-dimensional Euclidean space. This capital X set can also be possibly only the bounds of the variables. So several abstract things can be put inside the set capital X, irrespective of it is easy to present or difficult to present. But you have a flexibility that any of the constraint which you could present by inequalities, you can take that inequality also inside the set capital X. Fine. So here capital X is a non-empty subset of the n-dimensional Euclidean space Rn. So this is typically the problem generic constraint optimization problem. And here in our course of study, unless otherwise specified, we will assume that the functions f and all the functions gis and hs, they are continuously differentiable inside the set capital X. That is an assumption we make deliberately, because depending on the derivatives of all these functions, it is easy to identify a necessary optimality condition. And let me now mention a few terminologies related to this constraint optimization problem. We say the function fx as the objective function, and the functions, those are giving inequality constraints and equality constraints. All these functions are known as constraint functions. Then the set of all points in the set capital X, for which all the restrictions, all the constraints gix is less than equal to 0 and ajx is equal to 0. This is for all I and for all j. That means all the constraints. By constraints I mean this set of points for which gix less than equal to 0 and set of all those points for which ajx is equal to 0. These are the constraints. That means you are not unrestricted to lie inside your set X, but also there is a restriction, constraints or restriction. There are restrictions for this kind. Let's suppose this is your G1, this is your G2, and this is your, let's suppose, H1. And let's suppose this is my constraint set. This is my restricted set on which I am to identify a local minimum for the function fx. And that's why these functions gi, aj, those are called as constraint functions. The set of all points small x's inside the set capital X such that all the constraints are satisfied, that means set of all these dotted points, this set is known as the feasible set of the problem. Feasible set. And any point inside the feasible set is called a feasible point. Fine. So these are the few terminologies. Those will be required in due course. And also let me define a very important set that is called as active set. And this active set is the collection of all those indices at a point x0 that is feasible. So we let x0 be a feasible point, and you construct the set of all indices, set of all i's in the inequality indices 1 to till m, such that the ith inequality equal to 0. When this set of all indices, this a x0, is usually referred as the active set. And this active set has a very special significance. It says that if a constraint is inactive, let's suppose I have some I which is inactive, then what will happen corresponding to this I? Let's suppose gi x0 is less than 0, and this is my surface for gi x is equal to 0, and let me say this is my set gix less than equals to 0, this side, let's suppose. Fine. Now if I am at a point at which gix is strictly less than 0, let me say I am here, this is my x0, and at which obviously this particular I is not active, and therefore what is possible is at this point you can at least move a bit, maybe very small, such that you can move a bit can still be inside the feasible set. That means at a point x0, if you have gi x0, then from x0 there exists a direction d, such that from x0 you can move along the direction d, but still you will be inside inside the restriction that gix is less than 0. You will be still inside this gix less than equal to 0. And that is the special significance about the active set and inactive set. If an index I is inactive, then it is possible that there exists a direction D such that along the direction D you can move from the point x0. Still you will be satisfying this inequality that gix is less than 0. So then it is possible to move from x0 at least a bit without violating gix less than 0. Fine. Now, with these few notions, let me discuss the notion of cone of feasible directions. To discuss the idea of cone of feasible directions, at first I need to discuss about the meaning of a feasible direction. By a feasible direction, I mean a direction is called a feasible direction at a given feasible point x0 belonging to the feasible set f if there exists at least a line segment at least a directed line segment from the point x0. So let's suppose my feasible set is this set. My feasible set is, let's suppose, let me typically draw a feasible set. Let me say this is my feasible set, capital F, set of all points inside this bounded region. So this is my set, capital F, say. Now a point x0 is given to feasible, and at x0 a direction D is called feasible if there exists a line segment starting from x0 along the direction D such that that line segment is wholly lying inside the feasible set. Now mathematically, how can I present this? Mathematically, it says that if there exists a distance in the line segment, directed line, this emanated from x0 and along the direction D, there exists delta such that you have x0 plus tau D. Here x0 plus tau D obviously is a point in this line, right? Tau D still belonging to the feasible set for all tau belonging to the closed and bounded interval 0 to delta. Fine. And by that we mean it is a feasible direction. For instance, in this feasible set capital F, let me consider a few points and identify a few feasible directions. Let's suppose if my x0 is this location, then obviously any direction you take up is a feasible direction, right? Any direction you take up is a feasible direction. However, if I take a point on the boundary, let me consider a very specific point. Let's suppose this particular point. And you know that this is a feasible point, this is a feasible direction, this is a feasible direction, this is also a feasible direction. However, this is not a feasible direction. This is not a feasible direction, right? And therefore, at this point x0, the set of all feasible directions are the directions starting from this tangent to the boundary and this tangent to the other boundary. So any direction you take up in between this red dotted region, you note that any direction you take off is a direction that will keep us inside the feasible region, whatever direction you take off. Here this red direction is the tangent to this boundary at the point x0 here, and this red line is the tangent to this boundary. Fine. Now let me consider a point. Let's suppose I consider a point over here. Then at this point you note that any direction which is lying above this tangent line, let me say this is my tangent line on the boundary at the point x0, and here you note that if this is the tangent, then obviously any direction you take up just above of this tangent line, obviously that will lead us to be inside the feasible region, and therefore here set of all points, all these directions are constituting the feasible directions for the point x0. So these are enough examples. I will have some algebraic expressions of the set, feasible set, and then we will have several examples for this. But this gives us the geometric intuition of the feasible directions. Now with the help of the idea of feasible direction, now you consider at a feasible point set of all directions those are feasible, and these will surprisingly constitute a cone, and that cone is called a cone of feasible direction. Let x naught be a feasible point. The set of all feasible directions at x naught is called cone of feasible directions at x naught, which is denoted by, will denote it by CFD at the point x naught. FD is the shorthand for feasible direction. And then obviously that is, if I present it algebraically, then CFD at the point x naught, set of all those directions in Rn such that corresponding to the direction D, there exists a delta depending on obviously D greater than 0, such that x naught plus tau D is belonging to feasible region, and this has to happen for all tau belonging to 0 to delta. Fine. This is the definition of cone of feasible direction. Why is it called a cone? It is called a cone because you can easily prove that if D is a direction of this set CFD, if D is a direction in CFD at the point x naught, we note that obviously that will imply for any lambda greater than 0, lambda D will belonging to CFD at x naught. Very easy to check, you check. And therefore CFD evidently is a cone. Not only it is just a cone, we can also prove that origin must be belonging to this cone of feasible directions. Fine. And therefore it is a cone consisting the null direction as well. And this cone of feasible direction is also referred as in optimization literature. It is also referred as radial cone. So they are interchangeably used. Now let me put it as a note 1. Now next note, we note that if, let's suppose you have D belonging to CFD at the point x naught. By the definition, what does it say? Then it says that for all I belonging to the active set, for all I belonging to the active set Ax naught, by that what do we mean? By that we mean Gi x naught is equal to 0, right? So here you have Gi x naught is equal to 0. Fine. And if D is a feasible direction at the point x naught, you are at this location x naught, then D is a feasible direction. Obviously then you have a length of amount, this much amount, and that signifies, let's suppose, delta amount, such that x naught plus tau D is belonging to the feasible region for all tau belonging to 0 to delta, if D is a feasible direction. That is the definition, right? And what is the meaning of this belonging to f, x naught plus tau D belonging to f? Obviously then x naught plus tau D is a feasible point, and if it is a feasible point, then obviously you have Gi x naught plus tau D is less than equal to 0 for all I, and as well you have Aj x naught plus tau D is equal to 0, and this is for all I, this is for all j, right? Now I consider only those i's for which gix naught is equal to 0. For them, an interesting fact is going to happen. For all I belonging to ax naught, you have gix naught is equal to 0. And if I now consider gi of x naught plus tau d, as gi is assumed to be continuously differentiable, I apply here the Taylor's theorem, Taylor's expansion, first order expansion, and I get here grad x naught transpose d plus small o of tau, right? I get this one.
Notice here that this quantity is less than equal to 0
because x naught plus tau d is belonging to the feasible region, and therefore gi of x naught plus tau d is less than equals to 0. Therefore d belonging to cfd x naught implies for all I belonging to ax naught you have this equality true. Once you have this equality true, this implies the following interesting fact, that what you have here, if I divide on both the sides by tau, then gi of x naught transpose d is equal to gi x naught plus tau d divided by tau plus small o of tau divided by tau. Let me here remove the point 0 in the expansion, because 0 has no meaning in the expansion. Because if you have tau is precisely equals to 0, then both the sides are nothing but gx naught equals to gx naught. Now passing the limit as t tends to 0, as tau tends to 0, 0 plus,
then in the left hand side we have this expression.
and on the right hand side what is happening? On the right hand side, this term, you note that tau is always a positive quantity, and on the numerator you have a quantity that is less than equals to 0. Therefore if you take the limit, then this limit is less than equals to 0, right? And this limit evidently is existing because we note that if you take limit on both the sides, the limit for this exists, the limit for this exists, and therefore the limit for this must exist. And gi of x naught tau is then less than equals to, this quantity is less than equals to 0, and this quantity moves towards 0, and therefore you have for all I belonging to ax naught, you have this is true. Similarly, from this inequality aj x naught plus tau d equals to 0, you will find that gradient of hj x naught transpose d is equal to 0, and this is going to happen for all j. Fine. So let me neatly write the note 2. The note 2 says the following: if d belonging to the cone of feasible directions at the point x naught, then you have the following: and now depending on this set of all those directions, those are satisfying the first as well as the second condition in this system of equations, we define a new cone that is called as the linearizing cone, and that is defined as follows: let x naught be a feasible point, the set defined by set of all those directions in Rn such that gradient of gi x naught transpose d is less than equals to 0 for all I ax naught, and gradient of hj x naught transpose d is equal to 0 for all j is equal to 1 to till L. This is called as the linearizing cone, and this is denoted by CL at x naught is equal to this set, and this set is indeed a cone. You can easily verify it, that you take any d that is belonging to this set and you can easily prove that lambda d is belonging to the CL x naught for any lambda greater than 0. Anyway, so this set is called linearizing cone of the set or of the problem that we have considered here. Let me name this problem as constraint problem. So let me just name it as P. Fine. Now let me come back to linearizing cone. Is called linearizing cone for the feasible set F or of the problem P at the point x naught. Fine. Well, let me now mention a very trivial but important fact, that when I was trying to introduce the idea of linearizing cone, I started the discussion with taking a D from CFD, right? And ultimately, what am I going to get is that if D is inside the cone of feasible directions, then in that case we have this system of equations true, inequality and equality, and this system of equality and inequality in fact is coming in the definition of linearizing cone. And therefore you take any direction D in CFD, cone of feasible directions, that must be a subset of linearizing cone at the point x naught. Now here question comes, you may feel the following, the reverse might be true. That means you take a direction D in the linearizing cone CL and you may feel that D is belonging to the cone of feasible directions. However, this is not really true. For that, let me give you a counter example. We'll see that CFD x naught is not equals to CL, and therefore I will just consider an example where CFD is strictly a subset of CL at x naught. If you would have CL at x naught is a subset of C of FD, that means any direction in CL is an element of CFD, then that will prove what? If this is happening, then together with this will prove that CL and CFD they are equal. Now if I can give an example where CFD is strictly a subset of CL, then obviously this is not valid, right? This is not valid. Now let me give you an example for this, that you consider the following set. Consider the following feasible set. Let me consider a problem for which you have the feasible set F as the following. And take x naught as the point 0, 0. Obviously, this x naught is belonging to capital F, so it is a feasible point x naught. Now at the point x naught, let us try to find what is the set of feasible directions and what is the linearizing cone. If I consider the first inequality, let me consider the corresponding equality and graph, then I will identify which region, which part of that graph will give the inequality region. Here it is nothing but x2 equals to x1 cube. Graph is something like x1 cube, where 0 is a point of inflection. And on the left hand side I don't need to draw, because this left hand side is not inside the feasible region, because x2 is greater than equals to 0. And therefore let me just draw only the upper part. Now which part is your x2 minus x1 cube is less than equals to 0? Let me pick up a point here. Let me say 1 0. 1 0 is obviously satisfying x2 less than equals to x1 cube, and therefore this is the part. So this is your feasible region. This is your feasible region. This part, x2 greater than equals to 0 and x2 is less than equals to x1 cube. Now from this figure you can quickly identify what are the directions those are feasible. Now here you can find that as x1 axis is tangent to the graph of x2 equals to x1 cube for x2 greater than equals to 0. So for this curve you have the tangent, this orange direction, right? And therefore any direction that you take off apart from this tangent direction, let me consider any other direction, let me this direction is not feasible, right? And any other direction in the first quadrant is not a feasible direction, because any other direction will lead me to be outside of the feasible region. So here the direction, this positive x1 axis is the feasible direction. CFD, feasible direction at the point x0, is the set of all directions d1 d2 belonging to R2 such that you have d2 equals to 0. Not only d2 equals to 0, because the negative x1 axis is also considered in d2 equals to 0, and therefore you will have d2 equals to 0 and as well d1 greater than equals to 0. This is the only direction which is feasible at the point x0. Fine. And what is your linearizing cone at the point x0? Now to find the linearizing cone, you have to at first find what is the active set at the point x0. Active set, a set of all those indices of the inequality constraints for which you have gi x0 is equal to 0. Now at the point 0, 0, we note that the first inequality, if I write it as g1x, then g1 x0 is equal to 0. Similarly, if I write it as g2x, then g2 x0 is also equals to 0. Fine. And therefore both the indices 1 and 2 is the set ax0. And once you have 1 and 2, both of them, then we can easily identify what is CLx0. CLx0 is a set of all those directions d1 d2 belonging to R2 such that, and this will constitute the following. What is the gradient of g1 at x0? Let you just put the values of grad g1 x0 and grad g2 x0, and accordingly you will find that the CL x0 is the entire x1 axis. Fine. And therefore we note that this shows that CFD is strictly a subset of CL. Although we have started the linearizing cone definition from taking a direction from CFD, and then we have found that D belonging to CFD will imply that D is satisfying this inequality, D is satisfying this set, and this set is now in the definition of linearizing cone. Now here you note that linearizing cone definition is not assuming that let you take D from CFD, because here in the definition of CL you have D any direction in Rn such that D is satisfying these two inequality and equality, right? And that is the definition of linearizing cone. And we observe that CFD obviously by the definition is a subset of CL, but CFD is not equals to, in general, not equals to the linearizing cone. Fine. With this, next let me define the idea of the cone of descent directions. Descent direction is related to the objective function, and for descent direction we know what is the definition of that, and therefore I am not repeating what is the meaning of a descent direction for a given function f. Let me directly define the cone of descent directions. Cone of descent directions for any element not necessarily feasible, because descent direction is nothing to do with feasibility. Descent direction is related to the objective function, decency of the objective function, and therefore I take a point that might not be in the feasible region but inside the constraint, abstract constraint capital X. So let x0 is inside the set capital X, then the set, this set of the directions in Rn for which gradient of f at x0 transpose is less than 0, this set will be denoted by CDD. DD is the abbreviation of descent directions. We can easily check that this set CDDX0 is indeed a cone, because any D that is a descent direction, that will lead us to have lambda D is also a descent direction for any lambda greater than 0, and therefore the set or this cone defined by this is called cone of feasible directions of the function f, or we are related with the problem of the problem p at the point x0. Fine. Here you note that the cone of descent directions does not include the null vector. Null direction is not inside the cone of descent directions. Fine. Now we are slowly towards moving towards identifying a geometric necessary optimality condition. At least the first geometric necessary optimality condition can be derived with the idea of these three cones: cone of descent direction, cone of feasible directions, and the linearizing cone. Before that, let me mention a very important fact, that if D is a descent direction at the point x0, then what will happen is the following. Then if I consider to expand f of x0 plus tau d, where tau is greater than 0, if I try to expand first order Taylor's expansion, then I am getting fx0 plus tau times gradient fx0 transpose d plus small o of tau. Then we are getting and this small o of tau divided by tau, tau tends to 0 plus gives us 0, and therefore there is no term after this, so this is plus 0. And as grad f x transpose d is strictly less than 0, because this d is a descent direction, and therefore you have right hand side of the last equation is less than 0. And here you note that as this function is a continuous function, because here af(x0) is a constant and the function af is continuously differentiable, so f(x0) plus tau d obviously is a function of tau that is continuous, and divided by tau you are considering, or just you forget about continuity of this entire function, but at least the limit exists. So here it says that if I am considering this function as theta tau, that then limit tau tends to 0 plus theta tau is less than 0, and from the notion of limit, therefore we can find a neighborhood of 0. That means there exists certain delta greater than 0 such that theta tau is less than 0 for all tau belonging to 0 to delta. This is due to this fact of calculus, that if limit extends to some a of a function, let's suppose g of x, if this is less than 0, this will imply that there exists a neighborhood of the point a such that gx is less than 0 for all point x inside the neighborhood at the point a. Due to this fact, you have the last conclusion, this is true, and therefore you have note that 1 by tau f of x0 plus tau d minus f of x0 is less than 0 for all tau belonging to 0 to delta, and this will imply, as tau is a positive quantity, this will imply that f of x0 plus tau d is less than f of x0 for all tau belonging to 0 to delta, right? And once you have this, then this implies that for any direction d in the cone of descent direction, the function f can be reduced. This is actually common fact for the descent direction that we have discussed earlier, that f can be reduced along D at the point x naught. And if this is so, then we note that if there is a direction D that is common to feasible direction at the point x naught, as well as this is also a decent direction at the point x naught. If this is happen, then obviously you note that the point x naught cannot be a local minimum, right? Why x naught cannot be a local minimum? Because once D is a feasible direction, let's suppose I have my set, constraint set is this set, let's suppose, set of all these points, and you consider a point x naught. Let's suppose this is my point x naught, anywhere you take inside the set, inside the constraint set, uh, capital F. And now here, if D is a decent direction, then what will happen? Along this direction you can reduce the function, and therefore functional value along this direction, if you can reduce, then functional value at x naught is obviously bigger than the function value at least one point in this direction. Fine. And therefore the point x naught cannot be a local minimum. And these implies, then this note implies the following geometrical fact: necessary optimality condition. CFD x naught intersection CDD x naught is equal to null. If x naught is a local minimum of the problem P, then this must happen. Because if this is not null, then you can reduce the function value along the direction D. If D is inside this intersection, if this intersection is not null, then you have a D. Along that D you can reduce the function value, and therefore at a local minimum of the problem P you must have CFD intersection CDD is equal to the null set. There cannot be any common element. Fine. And here, as we are not describing the optimality condition with the help of the algebraic expression of the CFD and CDD, and that's why it is usually referred as geometric optimality condition. Here I have named the theorem as necessary optimality condition. Obviously it is necessarily true, but in order to ensure that it is really a necessary, not sufficient, I must have to give an example, right? Now let me consider an example which will say that the condition is indeed necessary and it is not a sufficient condition. So I make a remark here. The condition CFD x naught intersection CDD x naught is equal to the null set is only a necessary optimality condition, not sufficient. That means we will show that this condition is valid, that intersection is null, but the point x naught is not a local minimum. For this, consider the example. Minimization of the function f x1 x2 subject to x1 square plus x2 square minus 1 is equal to 0. And for this problem we will show that CFD x naught intersection CDD x naught is equal to phi at the point 0 1. Then you note that what is your CFD and what is your CDD. The circle that constitute the feasible region is this circle, and here if I take this point, this is my point x naught, and this point you note that at this point what is a feasible direction at this point, and you note that at this point you don't have any feasible direction, because whatsoever direction you take out, whatsoever direction you take out, that direction obviously is not leading us to be satisfying the constraint, because here the feasible region is only the equality region. Had the constraint set be inside circle, then obviously this direction is a feasible direction, this direction is a feasible direction. However, here the feasible points are only the boundary points of the circle, and therefore you note that set of all feasible directions at the point x0 is a null set. And therefore whatsoever be your CDD, you have CDD x0 intersection CFD is equal to null set. But is the point x0 a local minimum for the function x2? Obviously no, because you have a minimum value over here, and at the point x0 the function value is equal to 0, and you can reduce the function value till -1. Fine, and therefore the optimality condition, that intersection of the cone of feasible directions and the cone of descent direction, is indeed not sufficient optimality condition. Fine. Now with this I end up the class here, and on the next day I will consider to discuss about tangent cone of the feasible set at the point x0, and from this tangent cone we'll find another geometrical optimality condition that is more robust than this optimality condition, because this optimality condition is little restrictive due to the limitation of the definition of the cone of feasible directions. I will discuss what limitation you have. Limitation, obviously it is evident here, that you note that if the constraint set is just a curved surface, like here the constraint set, it is just a curve and not inside the curve, right? So if you have the feasible region only a curve or a curved surface or a curved hypersurface in the n-dimensional Euclidean space, then in that case what will happen? Most of the cases you will find that this CFD is a null set, and therefore what you will have, what you will have here, I am making a mistake. This is not the null set, because for the feasible set, you know that cone of feasible direction, it consists always the null vector, and therefore it consists the null vector. But CFD cannot consist the null vector. It does not include the null vector, and therefore this intersection is indeed null. Anyway, so as cone of feasible directions, cone of feasible directions, as it consists only a limited few directions, obviously it is very evident that out of those limited feasible directions you may not have a descent direction. Unless you have a descent direction in your cone of feasible direction, you cannot move your algorithm, because your algorithm should move in the feasible region, as well as algorithmic movement should be made along the descent directions. And therefore unless you have quite a few directions in your feasible directions, you cannot move your algorithm. However, to rescue this talking of the algorithm, that you have a very limited directions in the cone of feasible directions, we introduce an enhanced cone of directions that include the cone of feasible directions, and also that includes the essence of cone of feasible direction. We will introduce the idea of tangent cone at a point x0 on the feasible region. Anyway, so the thing about the tangent cone will be clear on the next day, and with the help of the tangent cone we will be finding a necessary optimality condition, another geometric necessary optimality condition, which is more robust than this condition, that intersection of the descent directions and feasible direction is equal to null. Now let me ask you a question here. With the question I will end up the class. And you note that the cone of feasible direction is obviously a subset of the linearizing cone, right? We have proven this fact. CFD is a subset of the cone of linearizing direction. and here you have for optimality you have CDD intersection CFD is equal to null, right? And you wanted to have more many elements in this set, because descent direction you cannot, this descent direction is not at your hand, you cannot include a new vector into it. Because why you cannot include a new vector? Because once the problem is given, the function f is given to us, and therefore descent direction, this cone is fixed, you cannot alter this cone of descent direction. And cone of descent direction is very important in algorithmic development, because along the descent directions only it is our attempt to move along with the descent directions, then only you will reduce your function value. And therefore cone of descent directions we cannot alter, and it is a fixed constraint cone. Fine. Now here are the attempts that you can, for a given feasible region, you can define CFD, you can define cone of linearization. Linearizing cone is a superset of the C of FD. Now as you wanted to have more many elements in your feasible directions, here can we have now as the optimality condition that CDD x naught intersection CL x naught is equal to null as your optimality condition. So my question clearly is the following: if x naught is a local minimum, does it follow that CDD x naught intersection CL x naught is equal to null? Let you think about this question. With this question, I am ending of the lecture here. On the next day, our agenda will be the discussion of the tangent cone at the point x naught. Then we'll answer this question that I am giving to you. You will verify whether it is null or not. And afterwards, with the help of this geometrical necessary optimality condition, we'll find one algebraic optimality condition depending on the gradient of the objective function and the constant functions. Fine. So those are the agenda for the next few classes. Well, thank you all for your kind presence.